So, yes, today I think I will be going slightly out of my comfort zone in mathematics, if I ever have one. And since I will be talking about the topology of modular spaces. So I hope it's not going to be too trivial for some people in the audience, but I mean, that's what I wanted to talk about. So in modular space theory, often algebraic stacks are constructed as quotients with respect to some action, some group action. And so if X is an algebraic variety and G is an algebraic group acting on X, the geometry of the quotient X quotient G is the quotient is the geometry of the action of G on X. And sometimes, if X and G are simple enough, just the fact of having a description as a quotient can let us say something interesting about the geometry of the algebraic stack. For instance, about its intersection theory by means of the method of equivalent intersection theory, or about its topology. So one negative example in this direction is the modular space of genus G smooth curves. When G is high enough, the corresponding algebraic variety is too complicated to give an appropriate description, to obtain something by the quotient description of such a modular space. But I mean, in low genus, something can be said. For instance, in the case of elliptic curves, this can be described as a quotient of X is the complement of a hypersurface with this equation in an affine space. This is basically the discriminant, and this is given by the Weierstrass equation. And G operates with weights four and 6 on the two variables. And this description is quite effective, and it's basically the description that Mumford used to give the first computation of the Picard group of this modular space, which is what? No, I say that it is true, but for higher genus, it's hard to draw some conclusions by this description. Okay. Okay. Besides that, I mean, after that, the theory has been developed, and the equivalent Char rings for M2 has been studied, and no bar. Yeah. Fine. Z12, yes. And also the spaces of a hyperelliptic curve has been studied by the same means by people like Vistoli and Fulgesu and Graham, Edidin, and Viviani. So today I wanted to speak to something similar, but in a different disguise. I wanted to speak about the modular space of trigonal curves over C, since I will be doing some topology over this modular space, and the modular space of trigonal curves, smooth trigonal curves. Smooth. Okay, so a trigonal curves is a smooth projective curve. I will consider only smooth curve for now, with a degree 3 map to P1. And so functorially, one can describe this modular space. If S is a complex scheme, then TGS is given by the family that are written this way. So where P2S is a pi1 vibration, is a conic bundle, and C to P is a flat triple cover, and CS is a smooth genus G family of curves. All right. So one particular feature of this modular space is that there is a forgetful morphism to the modular space of curves, or smooth curves, which is a locally closed embedding for genus bigger than 5, which basically amounts to the existence of just one G13. For instance, in genus 4, you have the quadric that cuts out two G13 on the canonical model of the curve. So the goal of today's talk for me will be the following. I will first introduce and give a very sketchy construction of the modular space of TG and show its Picard group. And then I will talk about the orbifold fundamental group of TG and its relations with the mapping class group, what is called the mapping class group, but basically it is the fundamental group, the orbifold fundamental group of the modular space of curves. Okay, so in order to construct this modular space, I will take the following data. So if C is a trigonal curve and F is the map, we can consider the direct image of the structure sheaf, and this decomposes as the O plus F, where F is a rank 2 vector bundle, and I take E equal to the dual of F, and I call, like in the literature, a Schirnhausen module. Okay? Of course, E is a vector bundle over P1, so it decomposes in OM plus ON. And there are two data that must be considered. M plus N for straightforward computation must be equal to G plus 2, and both M and N must be bigger than G plus 2 over 3 if C is integral. Okay? So more generally, there are theorems by Miranda and Casnati and Ekedal that give an equivalence. If S is a scheme, is a complex scheme, there is an equivalence of categories between the two following categories. The first is the category trip S that is given by the degree 3 flat and finitely presented morphism X to S, and the second category, which I call trip prime S, is given by the couples E alpha, where E is a rank 2 vector bundle over S, and alpha is a section of a certain tensor of the vector bundle, which is sim3 E O times that E dual. Okay, so there is an equivalence between these two categories, and basically the idea is that it is this section that gives the triple cover inside the projectivized vector bundle. Okay, so this is quite classical nowadays, and with Vistoli a couple of years ago, we basically used this data in order to construct the modular stack of trigonal curves. Okay, so this will be really sketchy, as I said before. First of all, we consider a stack TG hat, which is obtained as a quotient X gamma G, where gamma G is a certain product of linear groups. And xg is a vector bundle over a representation Vg of gamma g. Actually, to be more precise, it's a vector bundle over an open subset of this representation. But since the complement has a very high codimension, and we will be mainly interested in the Picard group, one can forget this somehow. Okay, so this quotient stack parameterizes couples the data, the datum E alpha of, that I defined before with the conditions given by the asterisk here. But unfortunately, it contains also singular curves. And since we are in, yes? Yes, no, this is more general. This is more general. This holds, this equivalence holds for a broader, I mean, as a complex scheme. This is more related to the particular case of triple covers of P1. Yes. Yes, it's the special case. It's okay. So this contains also singular curves. So if you want the modular space of smooth curves, you have to cut out something inside this scheme, inside this quotient. But on the other hand, the Picard group of this guy, it's very easily described because basically use the invariance under homotopy of the Chow ring, of the equivalent Chow ring of this guy, so you can contract all the vector bundle on the base, and then it boils down to compute the equivariant Picard group of the representation, which is basically the character group of this guy, and No. It is only triple covers. S is the scheme. Scheme. What are the categories? Yes, I mean the category over S. I mean all the triple covers of S of this kind. No, it is not the same S. It is not the same S, I'm sorry, yes. No, this is, no. No, it is not the same S. S is P. Oh, yeah, if you want, yes. Yeah, of course. S is P. You can consider pi 1 here. If S is pi 1, you get... okay? So you get the character group of this guy. Here I'm cheating a little bit because this one, it is a quotient with respect to some C star, and this is Z times Z. So at this point, if we want to describe the stack of smooth curves, we have to take out the hypersurface of there is an hypersurface dg in here, which is gamma g invariant, that parameterizes singular curves. So basically, in order to compute this Picard group, the only thing that one has to do, which of course it is not trivial, is to compute the class of this hypersurface inside the Picard group of TG hat. So using the exact sequence of a localization exact sequence, one gets that the subgroup generates. No, here I don't want to be very precise. So you have a representation of this group, and xg is a vector bundle over the representation, over over the representation. You have Vg, which is a representation of gamma g. No, xg. Xg is a vector bundle. You have an affine space, which is a representation of gamma g, and xg is a vector bundle over this. No, the fibers of vector bundle are more these spaces. Yeah, the spaces of section. Okay. Okay, so here it goes to the Picard group of Tg hat, and then the quotient, it is the required Picard group. So I'm not doing this. No, this is Tg hat. Yes, thank you. Yeah. Okay. Yes, it is in gamma invariant. Yes. Okay, it does. Yeah. So the pull back to xj. Yeah. Yeah. Inside. Yes. Of course. Thank you. Right. So basically, by computing the image of this z inside the z times z, we get the computation of the Picard group, which holds for genus bigger than 1, which is the following. It is z if the genus is not equivalent to 0 modulo 3, z plus z3 if g is equivalent modulo 3 to 0 and not equivalent to 3 modulo 9, and z plus z9 otherwise. Okay, and this is a joint work with Vistoli. All right, so this is basically a sketch of the construction and an application of this construction, but what I wanted to talk mostly today is about the topology of this moduli space, of this TG. So, moduli stack, yeah. I abuse. Right. So, in fact, the fact that it is a quotient will be helpful with respect to the calculation of its fundamental group, and also with respect to the mapping class group of curves of genus G. So, since it is an algebraic geometry conference, and myself, I'm not very much expert on the mapping class groups, I maybe will recall the definition of what the mapping class group is. So, the mapping class group of a Riemann surface of genus G, it is defined to be the group of the isotopy classes of homeomorphism preserving orientation. So if SG is a Riemann surface of genus G, then you take the group, you take the isotopy classes, the pi 0 of the group of homomorphism that preserve the orientation of the Riemann surface. And topologically, we have a description of the moduli space of curve as a quotient of the Teichmuller space with respect to the mapping class group. So the Teichmuller space is basically the space that parameterizes complex structure on a Riemann surface of genus G up to the action of the homomorphism isotopic to the identity. And there exists a properly discontinuous and not free action of the mapping class group on the Teichmuller space that gives such a topological description. In fact, since one has that the Teichmuller space is contractible, so one is tempted to say that the pi1, the fundamental group of the modular space, is exactly the mapping class group. And to some extent, this is true, but this must be stated not with the traditional pi1, but by means of the what is called the orbifold fundamental group. So I will define this object. I will define this object. So if X is a quotient stack or orbifold, if you prefer, where G is a group and X is a topological space, so the one has sorry, okay, and let EG over BG, the universal G principal bundle over the classifying space. So the orbifold fundamental group is defined as follows. It is defined as the classical fundamental group of the quotient of X times EG over G, and in X0 T, and T is any point on EG, since EG is contractible. Again, remark, EG is contractible. This allows me to take any T here. Okay, so in this sense, it has very much sense to state that the orbifold fundamental group of MG is the mapping class group defined above. Okay, so what is the motivation? I mean, one may want to study the orbifold fundamental group of subloci like the trigonal locus. The motivation is the following. So I will describe what happens in the hyperelliptic case. So HG is the modular space of smooth hyperelliptic curves. And so there is a natural, of course, there is a family of curves over HG family. And this family has a natural structure of homeo G principal bundle. That is, of course, the group of homomorphisms preserving the orientation operate on the fiber of this vibration. Okay, this is quite clear, and hence one can define a monodromy map from the pi1 of the hyperelliptic locus to pi0 of omeo G, which is basically the mapping class group. Okay, so basically what one takes a closed path in the base of the fiber bundle, and it associates the homomorphism of the base fiber associated by the lift to the vibration. Okay, it's a classical monodromy map, just as when you have a cover, but here you have a G principal bundle. Okay, what is striking of the hyperelliptic locus in this, with respect to this map, is that the map is not surjective. In fact, the image of mu GH is given by what are called the hyperelliptic mapping classes. That is the mapping classes that are given that commute with the hyperelliptic involution. Okay, so we wondered what is going to happen if one considers the trigonal locus, and quite surprisingly, what we remarked is that the monodromy map in the case of the trigonal locus is surjective, and this is what I want to show in the rest of the of the talk. So the idea is to find a family of trigonal curves with surjective monodromy. Okay, so, and the strategy will be the following. First, I will find a topological space, basically a complex variety, a Spunt complex variety, which has the right property to be surjective over the mapping class group. And then I will show that it carries a family of trigonal curves above. Okay, so I will start with a very fast remark. So if C is a triple cover of pi 1, if all ramification points are simple, then the cardinality of the ramification divisor is 2G plus 4. Okay, simple means that locally they are of type Z to Z square. Okay. So now I want to consider a hypersurface, which I will call calligraphic P, inside P1 times P2G plus 4, which is defined by the following equation. AI x 0 I x 1j. Okay, basically it is the hypersurface that parameterizes the universal family of forms of degree 2G plus 4 over pi 1. Okay, and of course this hypersurface defines a discriminant locus d2G plus 4 inside P2G plus 4, which parameterizes the sets of points where at least two of them coincide. Okay? Right. So I am going to consider the complement of this inside P2G plus 4. So basically it is the locus where all the points are distinct. Okay. So let me now consider the projective bundle pi 1 times u, the trivial projective bundle. Okay? So of course this is a homeo zero principal bundle because it operates. And I can reduce the structure group of this principal bundle to homeo 0 to G plus 4, which is the subset of the homomorphism of P1 that respect the intersection with the two G plus 4 points, basically. Okay. So it is a theorem of Zariski that the pi 1 of u with a base point, it is equal to the braid group of the sphere of 2G plus 4 strands. Okay? And the monodromy application, the monodromy map, the corresponding monodromy map that goes from pi 1 u to the pi 0 of omeo 0 to g plus 4 is surjective. And I will call this, of course, map to g 0, 0 to g plus 4. This is a theorem from Zariski from the 20s. And before going into action, I need one more definition. I hope not to abuse of your patience. If F, as before, is a triple cover with a simple triple cover ramified in 2g plus 4 point. So I will call omeo tilde 2g plus 4 the group of homeomorphism phi that lift to C. That is basically, I need a new blackboard. The homomorphism phi from pi 1, from P1 to P1, such that there exists phi prime from C to C, a homomorphism that commute with F phi, such that there exists. Okay, so this I will call homeo tilde, and if the cover is simple, then basically this implies that all the homomorphism in this group lift by simplicity. So we have a chain of group as follows, of a chain of inclusions. Okay. Right. So now I have accumulated enough data so that I can claim the theorem and finally try to prove it. So I will write it here. Basically, the monodromy map. Yes. I say that if the cover is simple, all the yes. Yeah. Yes. Faithful, you mean? Well, because you don't have automorphism of the covering, so all the automorphisms come from below, because by simplicity. You're not convinced? Okay, so yes, the monodromy map is surjective. Okay, so let me give a proof of this. I will denote M tilde, the mapping class group of omeo tilde of this. of the group of homomorphism that lives. And it is a theorem of Biermann and Weinrib that the index inside the mapping class group map 2G plus 4 of M tilde is finite. Okay? Okay, so now let us consider, let me call this map cross. Okay, let me consider the map there above cross and take the inverse image of this M tilde inside the fundamental group of U. So okay, this also has finite index. So this induces in a finite cover U tilde to U, and if we have used that projective bundle over there, so we can construct commutative square by pulling back this to U tilde. Say P is the finite cover. You can pull this back and obtain a and we obtain a projective bundle over U tilde, where we can reduce further the structure group by this inclusion. We can here we can reduce to the group homeo tilde 2G plus 4. So what is the upshot of this further reduction is that we can construct a monodromy map also for U tilde, and U tilde will be the candidate of for our surjective monodromy map for the trigonal locus. So basically you have pi 1 U tilde M tilde pi 1 U. This map is induced by the fact that U tilde is a finite cover, and here you have a surjective map to map 0 to G plus 4, which is the map cross of there above. And okay. Okay. So U tilde surjects on this mapping class group for the homeo tilde to G plus 4, and later I will show that it's easy to see that here there is a further surjection to homeo G, to pi 0 of homeo G. So it is our candidate to be to carry a family of trigonal locus that will have a surjective monodromy. So now I want to show that there exists, in fact, a family of trigonal curves over this complex manifold. So in order to do this, I will compare it to another cover of U, which is given by the Hurwitz space. So Hurwitz spaces parameterize smooth covers. In particular, I will take HG3. The Hurwitz space is the Hurwitz space of smooth simple covers of pi1. Okay, and it is well known. I mean, you can find it in the book of Harris and Morrison, probably, that Hg3 is an étale cover of U, and in order to compare U tilde and Hg3, we will compare the images of their fundamental group inside the fundamental group of pi1, of U, sorry. Okay? So, yeah. So we have pi1 of Hg3, the pi1 of U, and this map is induced by the finite cover. And there is a second map, which is once again our cross map that I described there above. Okay, so one composes this and gets a monodromy map for Hg3. Okay, so I can say something more on this monodromy map for the Hurwitz space. That is due to the fact that the Hurwitz space itself carries a universal family. So there exists a universal family CG3 over Hg3, and the existence of such a family basically implies that the map above factors through M tilde. Okay? Right. So this means that I can complete this diagram in this sense. This is the map that I've just discovered. Here there is a map induced by the finite cover, and since the pi1 of U tilde is the fiber product of the diagram, this induces a mu prime to this guy. Okay, and this mu prime is injective because it factors through this map, which is injecting since it is a finite cover. Okay, so what the upshot of this is that thus there exists a finite cover from Hg3 to U tilde. Okay, and I claim that this cover is an isomorphism. Okay, I mean the proof is pretty easy, and I can write it here. So basically, you start with two different covers, covers in the Hurwitz space, C and C prime, that go on the same point U tilde in the big space. Okay, so the fact that they go on the same point basically implies that they have the same set of homeomorphism of P1 of pi1 that lift. Basically the same set of homomorphism in homeo tilde. Okay? But if they have the same set, then they have the same ramification. And then by simplicity, they are the same cover. So the map is 1-to-1, and it is an isomorphism. Okay? So now in order to conclude, I only need to make 2 more remarks. Now I see that there is an isomorphism between the Hurwitz space and my topological space U tilde. So yeah, on P1, yes. Yes, I think so, because I mean, if you lift, it seems yeah. What could be? Yeah, 2 points. Exactement. Yeah. Yes, it's purely set theoretical. Purely set theoretical, but yes, it is so. It is purely set theoretical footage. Yeah. Okay. Okay. So, but moreover, the last remark I need is that all elements of omeo tilde to G+4 lift in a unique way to omeo G, since there are no covering transformation. Since by simplicity, okay, so this means that the monodromy map of the family of C3 well, now I can use indifferently HG3 or U tilde. Let me recall this U tilde factors this way. Okay, and this I know it is surjective by the diagram there. And the last thing to check is that this part is surjective. But this descends from a result by Hilden that said that if you have a simple ramified cover of the sphere, and all homomorphism of C is isotopic to a lift of an homomorphism of S2. But this is exactly the last statement that we need, because here we are talking about exactly the homomorphism of the curve of genus G, and basically this means that you can construct each of these guys starting from this one. And this concludes the proof of the theorem. Since I have maybe one... Yeah. 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 I don't know the proof, how it goes, but this is his result, yes. Yes, yeah, I see the point. I don't know how to do that. I don't know, but maybe, yes, I haven't cited my co-author, who is Michele Loenne, then maybe. And he's probably more entitled to answer this this particular question. But I think you can. I think you can. Yes, I don't know how, but I think you can. So let me just conclude by saying that it is likely that one can get some sublocus of the trigonal locus where the map is not surjective. In fact, for instance, say that this is a remark. Say if you take the locus where there are at least 2 points of ramification which are not simple. So say P and Q, then if you take the divisor P minus Q on the curve, then 3 times this divisor gives you a trivial divisor class, because 3P is linearly equivalent to 3Q. This means that over this locus, where you have two points of a non-simple ramification, you have a section. You have a section. Say, call this locus X. You have a section with the modular space of where there are more prim curves that parameterize curves with a 3 torsion point of the Jacobian. And since this is a finite cover of the modular space of curve, over this sublocus, probably you have a subset of the fundamental group, and this might induce a non-surjective map on the mapping class group. So another nice place to look at divisor where the monodromy map could not be surjective is the theta null divisor, for the same reason, because you have a section to the modular space of spin curves, and that is a finite cover of the modular space. So you have a subgroup of the fundamental group. So you may get not surjectivity. Okay, I think I will stop here. Thank you.
This Hilder result, does it apply to hyperelliptic covers? And how does it apply to hyperelliptic covers? They seem to be simple, right? Well, simple means that there is only
yes, this should work also for
each monodromy element is a simple transposition, right?
Right.
So it works for it should work for hyperelliptic, right?
Yes, as well. Yes.
At least if you so.
But I don't think you have the. I mean,
on the other hand,
I'm trying to reconstruct what could not work in the hyperelliptic case. I mean, what shouldn't work in the hyperelliptic case.
That was my question.
I think that you don't have this map. The one, the surjection, given that it's risky, I'm not sure that you have it.
Mm-hmm.
But I mean, it is well known that it is not surjective.
Yes,
I mean,
yes,
the image is known in the case of the hyperelliptic curve, and it is a proper subgroup of the mapping class group. So yes, it's a good question to see where this fails.
Okay, perhaps you can then tell that to me a bit later. Yes.
Whenever.
Okay.
Any other questions or comments? If not, then let's thank the speaker again.